Welcome back. Round 3. Ding ding. From recent experience, is it round 3 where both fighters get knocked down? So we might lose some people this week, one way or the other. So this is the last technical talk in that sense. So I'm going to focus on advanced methods. If you remember, the analogy last week was building blocks, a single house, and then a palace. So this week we're supposed to be talking about the palace, but I realised we didn't get through a lot of last week. So who managed to, between Monday and today, read some of chapter 2? Some people. Of the people that read it, any particular questions?
There was not much around the productionizing of the solution.
There is nothing about productionizing solutions.
Yeah, so
Neither will there be until week 4 onwards.
Okay, that's what I was interested in.
It ended with, we must productionize this, right? So actually the talk in the second half from Logical Clocks is talking about one particular example. There we go. Guest speaker at the back of the room. Everyone.
Just log and register to hops.site if you want to follow along. hops.site and click on the email you received, and then I'll let you in.
But no, in general, we'll talk about production issues in weeks 4 and 5. We're not going to talk a massive amount about the sort of production stack, though, in terms of trade-offs and decisions and from a tech perspective, right? We'll talk about what it takes to actually get something into production and what that might look like compared to a normal IT project. But I wasn't going to go through a whole load of product X versus product Y versus product Z. And although if there's a big demand for that type of insight, I guess we can throw something in. Any other questions? No. So I'm going to recover some of the stuff that I was intending to do last week. I also thought I'd give you a different view of, I only thought about this yesterday, but a different view of the course in terms of the first 3 weeks. So actually I think this book is a good kind of end-to-end introduction to some of this stuff. Yes, it's done from a technical perspective, but you can equally read the book without working through the code in Python. It will give you a flavour for what's involved. There are 2 chapters on it that are largely around production as well. So I gave you most of chapter 2, which I think is the legal limit of what I'm allowed to share. But I thought I'd characterise the content of the course slightly differently. So week 1 was essentially the preface and the first chapter of the book, give or take. I mean, taught slightly differently, but week 2 was largely going to be around chapter 2, which I've given you most of, in terms of pipelines and what are the different stages of processing. And then this week is basically the rest of the book. So, to put it in context, right? So the idea of this one is to take us from a sort of traditional 1990s to 2010 type understanding about what machine learning does, and then for the most part show you all of the stuff that's happened in the last 10 years or so in one fell swoop. I also realised that one of the examples I went through on the website, I hadn't given you the link, so if you didn't get back to the R2D3 example to walk through a decision tree, which is covered in a great deal of detail in sort of chapter 6 of this, that's the lightweight introduction. So I'm really going to take off in this lecture with ensemble learning, noting that we have skipped over training methods slightly, and if it turns out that later on we need it, I'm happy to go back over stuff, etc. I'll ask the same question next week for whether people understand chapter 2, and if there's more people with hands up saying, no, can we recover X or Y, I will absorb that into next week. So the main thing, the structure of the talk this week is how to deal with difficult problems, right? And we've seen a simple machine learning example, the decision tree, and the question is, what can we do to problems where that doesn't work particularly well, the sort of vanilla approach? So by and large, there are three ways to do this. There is making the problem simpler, and the techniques that we saw in the unsupervised layer, which were clustering and decomposition, are effectively ways to do this sort of thing. You can compress the signal to noise ratio, you can split the problem up into different bits, you can solve different parts of the problem at different stages in the pipeline. So we won't talk about that in great detail. But by and large, if you've got a really intractable problem, normally there's a way to split it into a less intractable problem. The first part of tonight's talk is going to be what do we do if we've just got a whole load of bad solutions. So we can't divide the problem into easier bits, but we can build upon partial solutions. And then the second half of the talk is how would we just build much better solutions in the first place, right? And the sort of deep learning architectures are, one way you could characterize them as just better models. So let's start. How do we find the answer to things in life if they're difficult?
Reframing the problem.
Reframing the problem? What if we've got a really difficult problem? What if we don't really know what the right answer is? Say that again? Gut feel. How do we solve this problem? Choose one. How do we choose one? Bad solution. Randomly. How else? What? Benchmarking. What have we been? What really, really complicated, knotty problems in the systems design? Think about human systems. What are the types of systems we end up with, particularly in this part of the world? Democracy. What do we do in a democratic process? We vote. So we could argue about whether the voting system is the right way to do it, right? But we are going through this tortuous process of voting for stuff. So, has he? Indeed. He didn't make the cut. So, if we've got if our classifier or our regressor, right, our machine learning algorithm or model is doing something but not doing a great job, what's the easiest thing we could do to make a system work better? Same answer. Vote. Like the simplest thing we could do is majority voting. So we take a whole load of different units, in this case predictors, right? And we could say, well, look, if they spit out here, 3 of them spit out the answer 1 and 1 of them spits out the answer 2, then perhaps we will go with the answer 1 as being the correct thing. How can that? What's good about that solution? Because you've got a majority. Given that the majority may end up voting for Boris Johnson, in that scenario, what are the sorts of things that we think might go wrong with majority voting? Bias.
It starts a series of wrong decisions
Starts a series of wrong decisions.
from this point onward
And how do we solve those types of problems?
by not making this decision.
By not making that decision. No, we basically come up with more and more convoluted types of voting systems. So we sample the population differently, and we have more complicated mechanisms than majority vote. We have things like first past the post, etc., right? And we've got a huge spectrum of political voting systems that are basically there to tease out what we think of as better, outcomes or better solutions to combining the outcome of systems that don't know exactly what the right answer is. And the same thing goes for machine learning. So there are a long list of these things, but I'm going to cover a few of them so you get a flavour. We're going to talk about bagging and pasting and boosting, which are basically ways that we can manipulate the data to get collections or sets of algorithms to work better together. And we're going to talk about stacking, which is basically how can we combine different algorithms together to get better answers. And the solution to stacking gets us into the structure of networks of predictors, and that will get us into neural networks in a slightly peculiar route. But then all of the rest of the talk's on the structure of neural networks, give or take, right? So that's how we get there. So if we're going to manipulate data, say we've got 5 different models using the same training data, and they do a good job, right, 95%. Do we think that's a good thing or a bad thing? How do we think they could do it? Why could they do it that way? Like, why would the answer for 5 of them, what could it possibly be better than one? Go back to political voting, right? Why do we think that one person's, the aggregate effect of lots of different people's votes is better than having the one person vote and make the decision?
It covers more use cases.
More use cases, in what sense?
I mean, the more data, the models from different data would have
The more, yeah, models of different data. So we think that a person is a model of data, right? It's that individual has sampled an experience of our societal economic system, and therefore will have a particular take on how that data should be interpreted. So the first thing that you can do is start to divide up your data differently. So far, we've given all of our data to the training algorithm, and the only thing that we've discussed in terms of partitioning data is for things like overfitting. So we'll keep the test set, and we'll keep a validation set, and we'll keep a training set. Keep those partitions. Now let's just focus on the training data, right? All of these tricks are basically how do we manipulate training data to get stuff to work better. So the first idea is bagging, which is if we take a random sample of data, we train an algorithm on different random samples, and if our sampling method is quote-unquote correct, then the errors that one algorithm makes shouldn't necessarily be correlated to the errors that another algorithm makes, and therefore something like majority voting would start working quote-unquote well. So that's a sort of trivial extension of how we would get generalization in a crude sense, scaled up. And the idea here would be that any one algorithm doesn't do a brilliant job. So this is a decision tree on a binary classification problem. It's a difficult one. I think it's called the Two Moons data set. It's a toy data set. The idea of a toy data set is something contrived so you can demonstrate the properties of the model, right? But this is quite difficult to separate because the data overlaps and there's no sort of simple partition of it. And a single tree ends up with a partition of the decision surface that looks like this peculiar thing, right? And the decision surface of a tree is always orthogonal to the axes, right? Because it's these stitching together these individual thresholds within the data. And so that tree does a particular job, but we can see there's lots of bits of it that aren't quite right necessarily. And using bagging, we train several trees, 4 or 5, but we do them on different partitions, and we add together the different decision surfaces, and we can see that we've got a better potential approximation to the curve. So what's one of the benefits of this method? What is the collection of votes doing that the individual decision or predictor is not doing?
Cancels out biases.
Cancels out biases. So what would be another way of saying that? Better accuracy, but in what circumstances? Less failure. I guess what I'm thinking about is generalizability, right? If any algorithm only sees part of the data, then you're going to get a certain different set of decision surfaces that are being modeled, but they should all have different biases. And therefore, when we get a genuinely unseen piece of data from a generative distribution that's unbiased, then hopefully it does a better job. What's a different benefit of sampling from the data? Potentially a different one. So we might get better generalizability overall. What's the corollary of generalizability? What's the the opposite effect we talked a little bit about, is this idea of overfitting. So again, if we only see part of the data, we're less likely to begin to radically over or underfit it. Overfit it. This is an example where, again, I just put this back into the examples with parabolas so you can compare it to the notes from week 1. This is an underfit example. So here we don't have many parameters and we end up only being able to fit an approximate line. This is one where perhaps we've got too many. We seem to be starting to model a lot of random noise, right? So this is the overfit solution. And if we use, this is to reiterate some of the stuff I was talking about last week, if we use a validation set and we train our model and we get to the point where the validation set error starts to go back up again, then perhaps at that point, that particular model, in this case the number of trees in a random forest, we get a smoother, better approximation than the overfit one, right? Here we're starting to get a lot of perturbations or modeling potentially of the noise process. If you go back to week 1, we think about that shaded area at the top of the curve, which is what's the difference between our model predictions and reality, or we had one outlier in a yellow point top right, looking at that diagram. What's the chances of that being correct or not? So, developing this a bit further, again, I'm trying to put some of this in context of historical development. So bagging and pasting techniques were well known from statistics in the same way that we worry about biased samples when we're thinking about voting in a population. The idea that you could manipulate sets of data to get better aggregate statistics, more believable statistics, was sort of well understood. But something as trivial as boosting, in the machine learning literature, didn't really come around until late 90s, 2000s. And all boosting does is say, well, if we're trying to model a set of data, why don't we do it iteratively, and we'll reweight the data such that the bits of data we get wrong, we weight higher when we refit the model next time. So here we're looking at a regressor. We start with some data. We go through a regression algorithm. We fit a line of best fit to the manifold of the data. And then we say, which bits of the data do we get wrong? And so here we've got an outlier because this particular point is further away from our line of best fit than the others. And so when we rerun the algorithm, we take that data point and we increase the importance of it. And that way, when we fit the algorithm the second time round, we don't fit the original data points as well, but we definitely fit the point that we got wrong better. And we can do this iteratively so that over time we get an approximation to the manifold that takes into account the likelihood that we get the points in the training set wrong or right. And again, we can moderate that the same way that we have before with the sort of validation set to try and understand what a good solution is. So put this in example, the first, unless someone from the audience calls out and says, I know the paper from 1963 or whatever it happens to be. But if you think back to something like Viola Jones' face detector in about 2003 or something like that, the first cameras that came out that put a box around the face, right? You hold the camera up and it puts a little, those were created using basically a tree-type algorithm that used boosting. And the early papers of this are comparatively they're recent, even something as trivial, you might think. Again, think about an example of what that looks like. Here's this same classification problem. This is looking at the iteratively as the data points are reweighted. So we start off with an incorrect solution, and we go down, and ultimately we get which we're going the other way around. This is our first solution, second curved solution, third curved solution. And you can see that we're slowly fitting better the shape of the curve. What's the difference between these? This is, if you think back to last week when we talked about learning rate, this is a learning rate that's high, and we've overshot the sort of correct model because the fifth iteration seems to be giving a demonstrably worse answer than, for example, the third one. Whereas here we've got a lower learning rate so that we are iteratively updating the parameters of the model and making smaller steps through the state space of the system. And here we're getting better convergence to something that we might think is a good solution. Question?
So instead of adding the data which is based on that outlier point, if we just add like a random sample data, what would happen? And basically boost it with the random data from the whole sample.
So you can do all of those types of things, right? You can play if we just think about bagging, we can play all sorts of heuristic games. There is some maths behind boosting showing that you're going to iteratively converge to a better solution in the end if we re-weight the data points in this particular style. There's all sorts of things you could think about doing, right? We've got 50 years worth of people, doing interesting, clever ideas, but there is some maths behind showing that that's the right way to do it. And similarly, the state of the art now is this idea of gradient boosting. So rather than re-weighting the original data for the errors, we look at the residual error from a model and we re-weight in the residual space. So, for example, here we've fitted a decision tree regressor, right? So we've got decision surfaces that try to fit the manifold of the parabola data, and we look at where it goes wrong. And so here, in this part of the decision surface, here we are making errors that are above the curve, essentially. And so if we look down here, in this part of the space, here we're in a different, we're looking at the difference here. Here we're above it. In this part of the space, we are below it. In this part of the space, again, we're above it again. And we will fit our new model, not in the original space, but we'll fit it in the error space. And so in the next iteration, if we add this decision surface, which ultimately, if all the errors go to 0, ends up being a straight line, i.e. easy, we add that back into the original surface, and we can see that when we iterate in the error surface, we're building up a more and more complete picture. So the state-of-the-art algorithms, there's a library called XGBoost, for example, on random decision forests. They are basically using gradient boosting. So we're fitting the decision surface in a variety of iterative spaces that model the error in the original space. Again, here I'm glossing over huge swathes of literature, because this is like decades of work, really. I'm picking out 3 examples, but you get the idea about how we could start with something that doesn't work particularly well and iterate to something that works a lot better. Following that, the last thing I was going to talk about is stacking. So those ideas, boosting and bagging and gradient boosting, are how do we manipulate the data space to be able to iteratively produce a better algorithm. Stacking is actually almost going back to the idea of voting, which is how do we just get algorithms themselves to work a little bit better. So we can take the original data set, we can divide it up, and then perhaps we can train different algorithms, but rather than just voting, which was the easy option, maybe in the same way that we used boosting to weight the errors differently, perhaps we can re-weight or learn a meta-algorithm that combines the outputs of the algorithms, which says that when you're in this part of the space, this algorithm is more likely to be wrong. And therefore, if we're thinking about a new data point that's here, we should downweight the output of those errors. These are almost like domain experts, right? In the same way that if you go to a tribunal or something, an ombudsman or something, right? You might still have an arbitration process that allows people to vote on what the truth of something is, but all of those people that are doing the voting are considered domain experts in some sense, and therefore, if the problem you've got is tax, you pay more attention to the tax accountant, and if the problem is employment, you pay more attention to the employment lawyer or whatever it happens to be. So stacking is a similar idea. We'll take a whole load of outputs, and we will learn when to trust the outputs of those individual algorithms. Now that can sort of be seen as a sort of meta-learning, right? In terms of blending the outputs, because really this here is another prediction algorithm. We've got a whole load of individual prediction algorithms with outputs, and then we have an algorithm that says, let's learn where to predict, where these predictors are predicting correctly. And you can generalize that to the idea of networks of layers of predictors, where you combine the outputs of those layers into the inputs of another layer that reweights and relearns, so that you can stack these things up, hence the word stacking, and you can continually learn a better approximation to the function through a series of different methods combined together. So that is, to put this in context, I think stacking as a meta algorithm isn't even implemented in scikit-learn yet. So it's quite common in kind of research papers, but there still probably aren't that many people in industry using stacking on an industrial scale. I have no idea what the numbers would that be. But the reason I've done it this way is because it gets you into this idea that we could start with a computation or a prediction, and we could start to add these things up to get more and more complicated predictions. That gets us into things like deep neural networks. So what we've covered to date takes us up to, say, 2010. Right? We've got a series of different classes of algorithms, regressors and classifiers and clusterers and sort of decomposition type algorithms, and you can piece them together in all sorts of different ways. And there are a few meta kind of learning algorithms like boosting or bagging that can be applied to these sets of algorithms in place to try and boost or improve performance. That process of sort of manually piecing together or only semi-automated processing steps together, it sort of can be thought of as feature engineering. Feature engineering is kind of a thing in its own right, which we won't go into in detail, but the idea is we can take some data, manipulate it to have a better indicator of the output that we're trying to predict. In the case in chapter 2, for example, it was, for example, taking one variable and dividing by another variable so that we had a price per square foot rather than just the absolute price and the absolute floor plate, right? That's feature engineering because we're feeding the quotient into the algorithm directly rather than asking it to learn the fact that the quotient of those two variables is important. Around 2010 onwards, we get into, let's call it mega stacking for the sake of argument. The other thing is I just wanted to put this on a timeline. So the odd thing about deep learning is, let's say it's sort of 2010 onwards, it's already into the sort of third wave of what we might think of as machine learning. So we've got the first wave, and you'll see in a second why I labour this point down here in terms of the sort of technical innovations in the 50s to the 70s. And I kind of glossed over all the people that worked on it here. It's okay, they also made very valuable contributions. But the origination of what we might think of as neural networks now, it predates Turing. It's ridiculous. I actually had to look this up on Wikipedia. So the work by McCulloch and Pitts that precipitates all of this is basically work on artificial neurons, a mathematical model for a neuron. And I'm going to ignore the sort of biomimicry component of this because I think it's a complete distraction. But the idea was that even before Turing had really got to grips with what a computation was, there was an idea that you could have a small functional unit that was a sort of a mathematical function and it would do useful work. Now that neuron model, or what's it called? I've got it on the next slide actually. Threshold logic unit is the basis, is the building block of neural networks, deep neural networks. And all we do is we combine computing units up in more and more complicated frameworks to get them to do more and more useful things. And similarly to the example, say, of a regression or a classification, is we take in some data, in this case inputs, and we weight that data, and we weight it, and we can learn the weights, which is we think this is data is more or less important. And then we threshold, or we have an activation function which says that, if, in this case, if the sum of the weights of the data gets above a certain threshold, produce an output. Now, all the early work is, so that's a computing unit or a neuron. The idea is that you would be able to combine these together to start to do logic. And so a lot of the early work was how do we produce logic gates, essentially, from these things. So there was the perceptron with Rosenblatt, and we get to the point where we start adding a few other bits and pieces, right? So we add in here some constants so that the computation at the activation nodes has not got just the weights and the input, but it moderates the output. And to put this into context, here's an example of an OR gate, an exclusive OR gate. So the idea here is that if we put data, x1 and x2, being two variables, into this space, you could go away and do the hand calculation. Right, for people that think this is interesting, which may not be many of you, you could go away and you could try this at home. Right, you could put some random values of x1 and x2 into a calculation, walk through, multiply them by a weight function, add in the bias, sum them up, and you'll see that the decision surface, in the same way that we've been talking about trees with a decision surface, the decision surface of this computing unit, in this case, is this surface between the 2 points. So there's lots of work on that in the 60s onwards, and then we hit a bit of a brick wall, which was that it was, quote unquote, proved that even though they were very flexible and you could produce logical circuits effectively from them in the same way that we can at a computer, that the structure of them wouldn't scale very well, and there were definite mathematical functions that they couldn't model. And one of the first gap in this sort of connectionist story was the fact that, do I have it labeled on here? Minsky. No, there's a famous proof that basically says, you can't get very far with these things. But it turns out that that was wrong, largely because we just weren't piecing them together in enough volume, in enough layers. So then we get to the point of having multi-layer perceptrons, and this is what would be thought of as a modern multi-layer perceptron. So we've got some inputs and some biases that can be learned. We've got we've got one hidden layer, which is a set of these computing functions, and we've got an output, and we combine the outputs and we threshold it. That really is the basis of everything we're going to talk about now. Why is that interesting? So let's go back to these models. That is interesting because this is a slide, a hand-drawn slide off one of Andrew Ng's Coursera classes. But the idea is that we could systematically build bigger and bigger and bigger models with more and more free parameters that are therefore capable of modeling increasingly arbitrary complex mathematical functions, which means that we just put data in, and if we've got enough data to be able to learn the free parameters, we can make it model any output, quote unquote. With the idea that as we get more and more data, we can, the performance of these models won't plateau. So if we have a traditional thing, a traditional algorithm, small number of parameters, we give it a certain amount of data, and then the limit of those parameters is such that it stops it being able to learn anything useful in the decision space. Whereas with a really big network, like a huge one, we'll come down to what huge means, if we have more and more data, the function can continue to be learned, and therefore we get better and better performance. So this is, I tried to start putting some better numbers on that kind of hand sketch. And this is definitely not correct, but to give you a sort of idea, which is that if you've got small amounts of data, let's say 100, less than 100 bits, then an analytical solution from the stats department prior to 1940, i.e. no computing, is still going to do as good a job in this low dimension, in this low data space. As we move up thousands of bits of data, you can start to throw some classical computing techniques at it, and we get into things like expert systems. And as we get into the 80s and the sort of standard GPU architecture, it goes up. And the idea is, as we throw more and more compute, gigaflops in this case, and as we go up through the layers of technology that can deliver it, i.e. now we're on TPUs, right? So tensor processing unit is a specialist chip that is being produced by, in this case, Google, but there's a sort of arms race for hardware going on. And as we go up and up and up, then the model performance, i.e. the complexity of the tasks that we can fit and therefore solve for goes up, but also the amount of data required to get them to work goes up. And so you've got this tension between compute, data and performance, that is these trade-offs. We talked a little bit, I'm going to revisit some of the anecdotal stuff from week 1 in terms of AlexNet, for example. 250,000 years to train was where we got to last time. I'll give you some other peculiar stats. So since 2010, the race has really been, let's call it 2012, has been how much compute and how much data can we throw at these problems. To give you an indication of what a state-of-the-art model looks like, each one of these units is multiple layers. So this is the state-of-the-art language model drawn out. And you can see it's definitely not 3 layers anymore. It is lots and lots of layers. And within those layers, you've got specialist units that are doing different types of combination, recombining data, reweighting data. And a lot of the studies in the last decade have largely been empirically driven, right? It's just, does it work? Yes. And so the theory is definitely behind where the experimental frontier is at the moment. And we're going to talk you through some sort of general ideas about the state of the art and massive models. How long have I got? Okay. So the first thing about these models is that you've basically got lots and lots and lots of different layers. And those layers might be doing specialist things, and you might recombine those specialist layers in different combinations. And the real state of the art is using a computer to basically search the right architecture, right? You get these neural architecture searches. So we will sort of use exploratory or even genetic algorithms to explore the possible space of large networks, to find networks that work well. And because the first thing that's happened is because these networks are vast and therefore take a lot of compute to train, a lot of the energy at the moment goes into how can I use a network that was trained for one thing and adapt it for something new. So how much, let's play a game again. Remember this game, the last answer was 250,000 years, okay? What was the cost of electricity for Google to train AlphaGo? Go back to this timeline, right? DeepMind, AlphaGo, 2016. It took a few months to train. So how much electricity did they use in a few months?
$500,000.
It's a good opening shot. I give you that. It's a good opening shot. It's the wrong order of magnitude, but... Next. Say again. Keep going. Not quite. Over 10 million. The figures are never disclosed. And that's just on electricity. It's got nothing to do with the team, nothing to do with running the offices, nothing to do with running the research, right? The amount they spent on electricity on GPUs and TPUs for training that algorithm was $10 million. Suddenly, a lot of energy has been put into figuring out how we retrain new models from existing ones. And a lot of these things have been open sourced. So if you think about some of the well-known vision algorithms like Inception, so Google released a vision algorithm called Inception, and all of the sort of, off the back of the release of that model, you've got a whole load of startups that are retraining that model for particular applications. They're building on top of it. We'll talk about technology moats in week 5. So one of the things that a lot of the tech giants are doing in terms of trying to dominate this space is to commoditize the infrastructure on which these types of systems are built so that they get vendor lock-in. So the idea is take an existing deep neural network for task A. In this case, we're looking at freezing. So we keep some of the layers the same. We choose a new task, and we just retrain the last few layers for this particular task. And therefore, we don't go back and use up all of the time and energy that was required to get this off the ground in the first place. Another thing that you're starting to see doing is that this is fine, but this here we're talking about supervised learning, so there's lots and lots of training data. Yeah.
When you say task, for example?
So, for example, Inception was trained on a random image base called ImageNet, and it might be that the applications are so broad. So, I have seen startups use Inception for looking at the electrical signal distribution on high-end Mercedes, so that they can produce an algorithm that adjusts the airbag velocity based on whether the passenger has put shopping bags on the seat or not. I have seen companies take Inception and retrain it for looking at the shadow patterns on oil wells so they can estimate oil stocks from satellite data. I have seen them retrain Inception for predicting the spectra pattern on Ebola field tests for predicting the presence or absence of Ebola in a medical test. So, completely different vision to end domain problems built on top of very large, generically chained deep networks.
Is it still using the same electricity though?
No. Key point is that all of the electricity cost is baked in. So if you keep all of these the same, you don't spend the energy, and you spend startup sums of money on retraining the head of it. Any other questions? The second thing that you see, this requires an awful lot of data. And by and large, for lots of problems, we don't have much labeled data, right? And so another thing that you're seeing a lot of at the moment is taking unsupervised or unlabeled data sets and bootstrapping those data sets up to the point where you get a very feature-rich representation that you can then stick a small amount of supervised training data on the top of, and again, retraining. So, for example, the state-of-the-art language models are, let's train on the whole of Wikipedia in an unsupervised learning fashion, and then let's find a specific task like find me fake news articles, and I'll label some fake news articles, and I'll stick that on the top, and I'll train for that, and it will be able to use the feature representation layer that's been learned off a completely unsupervised large public data source.
When you say it's just training unlabeled data, what is the end goal when it's training?
It is, you're basically trying to learn feature representations. So you could, for example, learn word embeddings on vast amounts of unlabeled data. It's used a lot in text because, in some sense, the text corpus is fully supervised in the sense that you can decide what word comes next because you've got the whole corpus. What's a good non-text example? I guess stuff that involves GANs, but we're going to come to GANs right at the end, so let's hold that thought. And you're even going to see some GANs trained, right?
It could be an example like if you had a cat, the probability of the word black appearing outside higher. So
Perfect. You're going to even get it firsthand. So those are some sort of general ideas that are going on at the moment on how to repurpose and reuse, and that's why certain types of very large algorithm have advantages. In reality, there is a vast collection of different structures of algorithms. And I've only hand-wavingly gone through the perceptron and a feed-forward neural network, and you could spend a lifetime understanding the architecture of all these things. And the state of the art is basically getting computers to search through the permutations of these different types of architectures, trying to find ones that are particularly good for certain types of problem. Again, the reason to put this into context, this is very much an empirical science at the moment. This is like chemistry at the turn of last century. If you think about the drug discovery processes, think about cases like IG Farben and the sulfonamide drugs, right? The idea was that we have these drugs, we know they're reactive. For example, we use them in dyes for clothing. We know they must have other properties, we've just no idea what they are. So we'll produce hundreds of thousands of tests of these chemicals on all sorts of things, and we'll just see where they land. And so a chemical that was originally designed for dyeing clothing turns out to be a chemical that's very good at curing a certain type of disease, right? And we didn't have good analytical chemistry to be able to go across those kind of design spaces. So the large companies just, in the sort of 1910s to 1940s, just systematically went through testing all of this stuff. And we've sort of hit that point with these technologies in terms of algorithms. You've got an arms race of systematically going through and trying to figure out what structures, in this case, model or algorithm structures as opposed to chemical structures, but what are they useful for, where do they work, when do they not work? We're not going to talk about all these models, these collections of models are basically modeling probability distributions over data in different ways, which we won't go into because it's incredibly technical. But there are some very easy things that we can talk about that are how can we exploit the structure of data? And so the first class of algorithms that I was going to talk briefly about are convolutional neural networks, which are largely designed for images. And the idea is that we can take input data in the form of pixels, and we know that there is implicit structure in that the proximity of pixels to the other pixels around it means that there is co-shared information. And so rather than putting in a single stream of pixels, let's put in the pixels in the way that they are captured as a two-dimensional projection of a world. And then there are a few different things. So this is a sort of generic CNN structure, and we have a convolutional layer. And the convolutional layer basically says, can we learn features over different scales in an image? We know that there is a certain amount of scale invariance in image. Like I put the pen up close, and it's large in your field of view. I walk back, and the pen, and it's small in your field of view, but I still know it's a pen. So there is an idea that we can learn by convolving images. And by the word convolution, I mean it's basically just learning weights again, but learning weights in a particular structure. And the second thing we can do is we can sort of build in some of this hierarchical representation. So we've put in something called a pooling layer. These algorithms were actually designed in the 80s. Largely originally by a guy called Yann LeCun, who's now head of machine learning at Facebook, just won the award. But they didn't work brilliantly for a long, long time. Again, we're waiting for the compute to catch up. So there's this max pooling layer, which basically says, can I iteratively compress my signal back down and learn structures over different scales in the image? And a real state-of-the-art algorithm looks something like this. I've mentioned AlexNet a few times in terms of, for example, training times. And reality, this is a, let's add this up. Whatever it happens to be, 48 layers or something, I think it is. But you get the idea that you've got these different layers in a network doing slightly different structural things, and they're being trained over large sets of data. And this is the performance on ImageNet, this large generic class. And you can see that in 2010, this is not working, right, at all. I think I showed this. Did I show this slide from week 1? So performance here is comparatively poor, right? We can't do something with it's only like 70% of the time. And then suddenly you get a dramatic drop-off to the point where in 2015, 2016, we're beating human performance on image recognition tasks. Interestingly, I don't have the graph. I haven't drawn it. Interestingly, for text, we hit that point on the 7th of June, 2019. That point in text data happened 2 weeks ago. So this is, you're talking very interesting times, right? Suddenly, on the standard benchmarks, humans are better at reading text and inferring things from text than humans. Weird, right? Anyway, this is an idea of the training times. I've been through this. But the point is that in the early 90s, this was hundreds of thousands of years in terms of compute power, and now suddenly these deep networks, we are down to tens of days or weeks for training times, which means that in that search space, we can iterate through that search space of possible solutions much more quickly, right? When the experiment time was in the order of years, let alone thousands of years, we still can't make much progress because you can't hold research teams together and you can't really learn from the outcomes of failed experiments. Whereas now that we're down into days, suddenly you can make a lot of progress. Why CNNs versus just normal deep neural networks? They tend to, the more structure that you can assume in the algorithm from the data, then in general, the fewer parameters you have to put into the model. So they tend to learn faster on image data because you're using the biases and the structure of the data to get them to work in the first place. Let's skip over that. What's the time? I just want to go back. We talked a little bit last week about thinking of a machine learning system as one that is optimized and iterates down into a better solution. So I wanted to revisit that. We talked a little bit about learning rates, so this idea that the solution will diverge if the learning rate's too high because we won't find the local or the global minima. And sometimes it can be too slow, and this is where we get it just right in terms of being able to get it to work. I wanted you to show you that in the context of a real deep neural network. I'm going to skip forward a few slides. So this is, ignore that for the time being. This is the error surface of a large deep neural network doing a real problem where we've only got, it's a comparatively shallow network, comparatively, still deep, but shallow. This is one where we have produced a much, much deeper network, effectively, in terms of structure. And we can see that the problems become more well-behaved and better, right? If we're trying to find this point, suddenly, in this network architecture, we can start all over the place and still end up in the right place. Whereas in this network architecture, we can, if we don't get it right, if we don't get lucky in terms of where we randomly start our experiment, we might end up here, or we might end up over there, or we might end up down here. Now, how do we find the right optimization thing is another reason why there was lots of progress recently on this. So there are a few tricks. Again, it's not really theoretically very well understood at the moment, but there have been a few tricks that have worked remarkably well. So one is dropout, which is if every epoch or every iteration of learning, we just delete or forget half of the values in the network, then we get much better convergence and much better behavior. Right? And this is weird. So this is like 2012, I think, one of these papers. If I do learning, but I ignore what half the neurons are supposed to be doing at any one time, I get a better solution. But the idea is that actually, when we iterate through this network, every iteration of the learning is learning a different random perturbation of the weights. So in the same way with boosting that we sort of randomly, or bagging rather, we randomly went through the data to get better generalization, here we randomly go through the weight space of the algorithm we're trying to train and we get a better generalization. And then there are a few other tricks, skip connections. So this is the idea that these networks have one or two particularly difficult problems in terms of things like catastrophic forgetting. So you train all the way up to a certain point in the deep network, and then the signal doesn't propagate any further, and you can't get other layers to converge and things like that. And so there is other sort of empirical engineering tricks, skip connections, which is that rather than connect all the way through the layers, we start to send the signal around some of the layers so that some of the original signal still gets deeper into the network structure. And I wanted to show you, actually I've forgotten, it's the wrong one. This will do though, but you get the idea. So that as we go through a particular, this is ResNet, this is one of those ImageNet algorithms. As we go through the different layers, we can move the signal around. So this is one section of a deep connected architecture, and we are sending the signal across different layers to get it to propagate through. That produces better results in general. Another thing that we have to do, just to be sort of mindful of, for these very deep networks is that we often don't have enough of the right data. So you get into things like augmenting data. So if we were trying to, in this case, learn the number 6 or the digit 6, we will augment our original example with transformations of the data so that we can give it 16 examples of the same data. And so there's a sort of dark, whereas before the dark art was in the original feature engineering, now the dark art is in the sort of data programming in terms of being able to give a very large algorithm enough of the right sort of training data. I'm going to skip this bit. This is the second one I was going to talk about in terms of recurrent neural networks. So we talked a little bit about time series. So in the same way that spatial data in terms of images has structure that you can exploit, time series data has structure that you can exploit, and you end up with different sorts of sequence prediction type algorithms, which are basically learning, what came before and what comes after. That we've talked about. And then the very state of the art, in the last 2 years, is that in the same way that transfer learning, or this relearning a large algorithm to give it small functional units, there's been a lot of work recently on this idea of multitask learning. So we have a very big network that's trained, using tens of millions of dollars. And then we can start to reassign it all different tasks so that we get deployable models that are just particular instantiations of a much bigger original model. So there's a lot of work on going on and trying to compress model architectures, being able to get it run on much smaller hardware, being able to get a run with much lower system requirements in terms of the data throughput, etc. Right. Let's wrap up. Bear in mind we were talking about building a cathedral out of Lego or King's Cross Station, right? So I've tried to show you the steps that people are currently working on to get these kind of state-of-the-art models. So we looked at supervised learning and we looked at unsupervised learning, and mostly the examples I've given have been supervised. But just to sort of reiterate something that we did in week 1, right? Supervised learning is where we know what the right answer is, right? We know what the right answer, we know what we want. So we can force the algorithm to give us the answer we want. Unsupervised learning is a little bit like we don't know what the right answer is, but if we saw a good answer, we would know how to evaluate it. In reality, there is a third sort of machine learning, which is reinforcement learning, which says we don't know what the exact right answer is, but it's not quite as bad as not knowing the right answer only in the case where we get to see a good one. We've got a way of measuring at every iteration how good the answer we provide actually is. So there's all sorts of work in things like robotics in terms of training machines to get better at a particular task, where there's a cost function, which is, if you do it this well, you get this reward, and if you do it, worse second time round, you'll get penalised, etc. And so I'm not going to cover this in detail. Mark Warner from ASI is going to talk a little bit about application of reinforcement learning problems in industry in week 5, I think, but to put it on your radar. And then just to wrap up today, if you think about reinforcement learning, I said I would go from ANS to GANs, and so a recent, very popular area of activity is this kind of reinforcement learning type model, although it's not a reinforcement learning algorithm strictly. But the idea is that we can, rather than just training these individual networks on individual problems, we can actually start to combine them together, and in this case, an adversarial way. So we have one network that is trying to learn how to generate data for a particular problem, in this case, how to create the image 8, and we can learn a second network that's trying to tell when it's being tricked by a different source of data. And you can train these things in an adversarial way and to basically bootstrap your way from having not very good data to examples of very good data. And in the same way that when we looked at something like stacking, where we were trying to combine the outputs of two algorithms, now we've entered a phase where we're sort of playing algorithms off against each other. We're now getting structures so that you can use the different capabilities of networks to give you an overall better solution. Right, so to wrap up, summary, what have we done so far? Weeks 1 and 2, we're basically going this data pattern algorithm model. So we go from data to patterns. We try and learn a model, and there are sort of 3 steps in learning a model. There is the choice of the model itself. What's the probability distribution? What's the parameterization? Then there are 2 algorithms, a learning algorithm and a prediction one. And ultimately, we go from, we get predictions from those models. What are we doing in the second half of the course? Organizational transformation innovation. We are going to do this part of it, which is kind of model engine application. So whilst we've got data in the model and it gives us a prediction, in the context of a business, we've got to turn that into an engine. We've got to deploy an engine. We've got to fit it in. We've got to get the engine and the prediction to fit into an application of some description. So I'll start talking next week about the sort of design decisions from a business perspective, about how to identify where this technology can be applied. So give me 2 minutes and then we'll stop for a break. The reading for the beginning of the second half of the course, effectively, is thinking about data as a strategic asset, right? These are technologies that allow us to start to manipulate and use data. And to do that, to walk through some of the use cases, I'm going to use something called a Wardley map. I showed you this briefly in week 1, but we're going to think about the structure of data, the structure of applications in a business setting, the structure, the infrastructure, and the orchestration required to actually do something in a business. And to do that, we're going to talk about a Wardley map. So the reading for this week is chapter 1 and chapter 2. It's approximately an hour. It's online. It's freely available. And that will mean that when we start talking next week, I don't have to explain what a Wardley map is, although I will run through it quickly. We can just get on using it in the context of designing predictive systems.